Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We are happy to have Anup Rao with us from UT Austin, and he's going to be talking about extractors for a constant number of polynomially small minimum entropy independent sources. I too have much too long titles of my talks, so but it tells us what you're talking about, yeah, which is great.
Thanks. So I should start, right?
Yeah.
Okay. Thanks for coming. So that's what I'm talking about. Here's the outline of my talk. I'll first introduce the problem that I'm going to talk about and state what the main results are, and maybe say something about why you should be excited. And then I'll tell you about the techniques and how I went about solving this. And finally, I'll say a little about what's still left to be done. Okay. So here's the basic problem in this area. So what we're trying to do is construct a randomness extractor. This is an efficient function that maps, say, n bits to m bits, with the property that for any weak source of randomness x, the distribution x of x, which you get by sampling the source of randomness and then applying this deterministic function x, looks close to uniform. Okay. So the standard way to measure the amount of randomness that's available in this weak source of randomness x is to bound the min-entropy of the source. So what is that? We say that a source has min-entropy k if the weight of the heaviest point that the source of randomness can give you is at most 2 to the minus k. Okay. So the goal is to find a single function which for any source of randomness, any distribution, which is not necessarily, you don't know anything about the distribution except that it has some kind of entropy, that it doesn't have very heavy points. And you want a single function that will turn this distribution into the uniform distribution. Okay. So if you think about it a little bit more, let's just imagine we're trying to extract one bit of randomness from a weak source. Then what you want is something like this. So this is the set of all n-bit strings. And what you want to do is you want to map some of the strings to 0 and some of the strings to 1 with the property that for any weak source of randomness x, what happens is roughly half the weight of the source gets mapped to 0 and half the weight gets mapped to 1. So if you think about this for a little bit, you realize that this is impossible. Given any function that you come up with, at least half the points will get mapped to either 0 or 1, and then there's a source of randomness, which has lots of entropy, for which this function will fail, right? Okay. So given that, a lot of the work has focused on placing more restrictions on the sources of randomness, which still give interesting problems and interesting applications. And the restrictions kind of received the most attention over the last 15 years is what I will refer to in this talk as the seeded extractor problem. So here you assume you're given access to our original weak source of randomness x, and you're also given access to a short, independent, truly random seed y. Okay. And now you want to find a deterministic function such that for any source x, the output of this function looks uniform. Okay. So under this restriction, extraction is feasible, and a long line of work has given really good extractors today. Okay. Now, any function on two inputs can be viewed as a family of functions on one input. So we can also view this extractor up here as a family of extractors indexed by the seed y, right? And we can ask for the slightly stronger property that for every source of randomness x, most functions in this family give you the uniform distribution, right? So if you did have a family of functions indexed by y, with the property that for any source x, most functions give you uniform distribution, then you do have, this gives you a seeded extractor, right? You use the seed to pick one of the functions in your family. But it's a slightly stronger.
The other one is a neo.
What?
This is,
I guess,
in the statistical
yeah.
physics terminology, this is the quenched problem, and the other one is annealed, which is easier.
Okay. All right.
Yeah, that's
Now, obviously, the most is allowed to depend on your on the source of randomness x, or is that not?
The
what, the most?
Yes, when you say most functions, so.
okay. So what does most mean?
Does
So
most mean?
right.
Is
So
the quantifier of, I mean, is the most before for all x, or is it for all x most?
You mean for a y?
no, it's
No,
almost.
the most goes over y. So
Yes,
I
for
understand.
most y.
it's for every x for most y.
Right.
Good, okay, so the y's that don't work are x dependent, of course.
Right. Exactly.
They-
Right,
they
so
have
this-
to be.
Right. So what we just saw is that for any fixed
Right,
y.
absolutely.
Right.
It
it's
has
you-
to be, yes.
Okay.
Yeah.
Okay, so on that also reminded me, I forgot to say that, so there are lots of parameters with extractors. An important one is the error, right? You're not going to get truly uniformly random bits. You're going to get something that's statistically close to uniform. And I'm going to ignore this issue for most of the talk, but you can ask me a question if you feel it's important. Okay, so anyway, so that's what a strong seeded extractor is. So that's how I want to view it for this talk. I want to view it as a family of functions with the property that given any single source, say 99% of the functions are good extractors. Okay, just to give you an idea of the kinds of what has been achieved for strong seeded extractors, it's not even the best one, but today we can, given a source that gives n bits with min-entropy, say n to the delta, some polynomially small min-entropy, we know how to build strong seeded extractors that use only a logarithmic amount of independent seed and extract lots of random bits. Okay, so and below again I've written the strong seeded extractor property a little bit more in a different way, right? So for a fixed source x, the probability over all y that the distribution x of x and y is epsilon close to uniform is high.
So TRE is probably Trevisan.
Trevisan,
But
this is
what's, and RRV is,
Raz, Reingold, and Badan.
okay.
But, yeah. Okay. All right. So apart from the so extractors have found lots of applications. The most obvious one is to weaken the assumption that we have access to truly random bits. Right? We can now run applications and protocols with access to only sources which don't have, which just have some entropy and aren't necessarily truly random. But apart from that, they've been used in coding theory, in approximability, and the reason I think we should study them is because I think they're fundamental combinatorial objects, just like expanders and epsilon bias sets and I don't know, almost k-wise independent distributions, and they somehow, if we understand how to deal with them really well, then maybe we understand randomness a little better.
So which of the three words have been trademarked?
All three of them.
All three there in bold.
In that little, and do you use the acronym and stuff, XCO?
Yeah.
You should trademark that too.
Right. Okay. Okay. So the model that right. So the seeded extractor model was the model that's received a lot of attention, but the model I'm going to talk about today is independent sources. So here the assumption is just that you have access to a few, in this case, say 4 sources which give you random bits, and you just know that they're independent. There are no correlations between the 4 sources. Okay.
No. So what does no correlations mean if they're not random?
So you have, you just have 4 distributions which aren't uniformly random, but they're independent.
Pairwise or totally?
No, all completely independent of each other. Okay. So it turns out, so you can show just if you pick a random function for your x here, then you can show that it is a good extractor for just 2 independent sources, even when the min-entropy is as small as logarithmic in the length of the sources. Okay, so the whole problem here is to find an efficiently computable polynomial time algorithm x that does that achieves the same kind of parameters.
How many bits can you extract?
You can extract something like k minus, not sure, but k minus little of k for sure. But I think you can hope for more than.
Is there some variant of the von Neumann trick that'll work with separate independent sources? With a single source, you can certainly do that. The bits are independent.
For a single source, the von Neumann trick, you mean this coin tossing?
The switching the order of things. To decide
If the original bits were independent.
Yes, but I'm
okay, I see.
Some way
That's a lot of it.
You need a lot of independent bits for that to work, and a very high entropy, right? So if you think about what's going on here, the entropy in the source, so you get a single source here is you get n bits, and there's only log n bits of entropy anywhere. So there's a lot of correlation across the bits. So it's a more general model. Yeah, so there are even better extractors for these. If you know that the bits are independent, there's another model of sources that captures that. It's slightly more general than even von Neumann's model, but it's a different problem, and there's been work on that too. Okay, so here's the long, big table of results for this area. You don't have to read everything. I'll just point out some things that should be noticed. So this model was first considered as far as in the 80s by Shor and Goldreich, who just showed that the dot product function is a good extractor for 2 sources when the min-entropy is pretty high, when it was like 0.6 times n. Right? Remember that we can hope for a term of log n in this column here. And then for a long time there was no real progress in improving the entropy requirements until in 2003 they were sparked by some results in additive number theory and some results in mathematics. There were results by Barak and Pagliazzo and Wigderson and some others that allowed extraction from a linear entropy from a constant number of sources of linear entropy. And okay, let me see. So the current best extractor, if you absolutely want to reduce the number of sources that you're working with, is by Bourgain. This requires only 2 sources of randomness, and it works for entropy that looks like 0.499 times n. So in a long time, there hasn't been much improvement in this.
But I would imagine his construction is a whole lot more complicated than a dot product.
The construction is not much more complicated.
No, it's not.
It's it's like a polynomial and then a dot product. It's, the analysis involves new results in additive number theory, something called the sum product estimate.
Okay.
But the construction is
analysis
simple.
was hard, but the function that you used was pretty simple.
The function is simple, yeah.
Okay.
It's just a polynomial, a degree 2 polynomial or something.
Okay.
What kind of function people had suspected worked?
Okay, and the result I'll talk about today is this one. This is again, so this one gives an extractor for, it was the first extractor that worked for a constant number of sources and polynomially small min-entropy. So for entropy k, you need log n over log k sources. So if k is a polynomial, this is just a constant. But it's not it has since been superseded by an extractor in this paper. This is myself with Barak, Shaltiel, and Wigderson. And the improvement in that paper is just that the error was improved by a lot, which is important for the application we're working with there. So anyway, this is the extractor that I'm going to talk about. It's an extractor for a constant number of sources and polynomially small min-entropy. Okay. So that was the problem. And now I'll start talking about the techniques. Okay. So first I'll need to introduce some concepts. So the first thing I'll need to introduce is the concept of a somewhere random source. So this is a more restricted model for a source of randomness. So somewhere random source is a source which gives you bits in the form of a matrix. In this case, a matrix with T rows and R columns. Okay, and you know that one of the rows in the matrix is distributed uniformly randomly. Okay, so in this case, the way this picture is drawn, the third row and the last row are uniformly random rows. So you get a sample from this matrix, and all the bits are correlated in in arbitrary ways, other than the fact that one of the rows is uniformly random. Okay.
And
this is Tashma. So he introduced this definition. It's turned out to be useful in work on seeded extractors before.
But the row is fixed ahead of time, right? It's not a random row.
The row is fixed ahead of time. You don't know which row it is, right? So I should say also that his original definition was more complicated. So I'm sticking with a simpler definition. So if you read some other stuff, it might be confusion. But
so the number of bits is R times T.
Number of bits is R times T. The min-entropy is at least R.
Sure.
Right. Okay.
So the other rows could be totally deterministic.
They could be deterministic. The second row might be equal to the third row. You don't know what's going on. Okay.
You require that your uniform random row is independent of the other ones, or
No. If it was independent, it would be the problem. Okay, let's think about
Then
it.
you could just extract those.
Well, you have to find it.
Well,
No, you could. If it was independent, what could you do?
So you
Right.
can XOR it.
You just XOR everything, and you'd be done. Right. So I guess if you want to think about it, the best way to think about it is as you have one random row, and every other row is some arbitrary function of this random row, and this is the most general. This is general enough. So if you can extract for that model, then you'll extract for every. Okay, so you have one row, you don't know where it is, and everything else is a deterministic function of that row. Okay. Another concept we'll need is aligned somewhere random sources. So if you have two somewhere random sources, we'll say they're aligned if there's some index where the random row is, both the random rows in that index are random. Both the rows in that index are random. So in this case, you have this somewhere random source, and the third row is distributed uniformly random. And here in this source, also the third row is distributed uniformly random. So these two are aligned. Okay. Okay. The point is that somewhere random sources are really nice to work with. They come with a bag of tricks. So let's start going through some of the things you can do with somewhere random sources. So here's the first thing you can do. So it turns out that strong seeded extractors already give us a way to convert arbitrary sources you don't know anything about into somewhere random sources. Okay. So what can you do? So here's what you can do. And not only that, if you have a bunch, if you have four general sources, you can get 4 aligned somewhere random sources using strong seeded extractors. So how would we do that? Well, so here's what you do. You take each source and you run over every seed that goes into the strong seeded extractor and evaluate that extractor on the source. So to get the first row of this source here, you would take this source and run the strong-seeded extractor with this source as input and the first possible seed as input to get the top row. Then you run it with the second seed to get the second row, and so on. Right? So if we ignore the rest of the other sources here, so what's going on? Because of the strong-seeded extractor property, we know that for any fixed source, most of these rows will be uniformly random or close to uniformly random, right?
Wait, but you only get log n of them and not fully.
No, log n was the seed length.
The seed length.
So they're a polynomial number of functions, so you get. Okay. So starting from a single source, we can convert it into a semi-random source that has lots of rows, polynomial number of rows, right? And since 99% of the rows are uniformly random, if we only have, say, 4 or 5 sources, then we can argue that there must be one common row that's uniformly random. Okay. So in this way, you can convert arbitrary sources into aligned semi-random sources. So this kind of shows that although semi-random sources. Okay. Yeah, I should have written it. Okay, so to get the first row here, the first row is obtained by evaluating the strong-seeded extractor with this source as input and the first seed, the all zeros seed, as input. Okay, so it's the value. So if you think of the strong-seeded extractor as a family of functions, then each row here corresponds to evaluating one of the functions on this source, right? So there are a polynomial number of functions. Each one gives you a different output.
Now, this is much nicer than your general setting, because not only does there exist a row, but actually if you choose one at random, it will typically be uniform.
Right, yeah.
Which is much nicer.
Yeah, but I mean, we're kind of going back. So how do we do that? We use a strong-seeded extractor, right? So we're just messing around with definitions.
At random.
Yeah.
At random is the problem.
We started off with a strong-seeded extractor, which already did exactly that. It picked one of these rows at random.
Yeah.
So I'm just basically restating the definition of a strong. But anyway, so the point is that semi-random sources are pretty general, right? In particular, you can convert any source into one.
So they're not hard to get, is what you're saying.
Right.
Given a strong-seeded extractor, then
right.
you get.
Given all this technology that's already around, yeah. Okay. So that's the first trick. The second trick is that suppose you have 2 aligned semi-random sources which have lots of rows. You can improve the situation. You can combine them to get a single semi-random source which has fewer rows. Okay. So how can you do that?
Yeah.
So this is okay. So I will refer to this operation as condensing. So given 2 semi-random sources, you can condense them to get a single semi-random source, which kind of has a higher quality, a fewer number of rows. So one way to do that is just with the XOR function. So suppose you have 2 aligned semi-random sources. You can just XOR the first row of the first source with the second row of the second source, and so on. And you see that somewhere in there is an aligned row. So we have 2 semi-random sources which are independent. It's crucial that they're independent. Okay. So if you have 2 independent semi-random sources which are aligned, then we can condense them to get a single semi-random source that has a fewer number of rows, right? So we'll just break up the sources into pairs of rows, and kind of XOR along the diagonal. And you see that at some point we'll be XORing something that's uniformly random with something that's independent of that distribution, right? So at that point you will get a uniformly random row.
So the independence is crucial here. You
Right.
mess up here.
Yeah.
Your rank.
Right. I mean, so without the independence assumption, you could always take a single semi-random source and get 10 by just cutting it. Okay.
So you're just saving one row?
No, we're reducing the number of rows by half.
Yeah, whoops. Yeah,
Uh,
because he's XORing all this stuff that's not.
So for every pair, you get 1 row.
Right.
Okay. So somehow, so on the left, we start off with two independent sources. We lost independence, but we gained in, right, you made it smaller.
So if you have k, can you just do a factor of k, or can you be more tricky and get something like 2?
If you have k, what?
Independent, aligned, somewhere random sources, and you.
Yeah, I know how to do. I mean, k. You could do k by taking clumps
So
of k.
he's saying, can you do,
Can you do
more
better by
independent?
sort of?
That's a great question because we are going to do much better, but it's not so simple as XOR. But we will get to it. So that's exactly how we're
But
going
there is, but what your construction involves is a way of.
Right. Is we will later on have a way of combining many of them and reducing by not just.
I don't think he was asking that whether you could do it with XOR, just could you do it in any way? And so
Yeah,
that's
you
what
can.
you're doing.
Right. Okay. So already, once we have these two tricks, we can try and build an extractor for independent sources. How? We could just try and condense until there's nothing left to condense. So we could start with a whole bunch of independent sources, okay, and then use our first trick to convert them into aligned semi-random sources with lots of rows, polynomial number of rows. And then, so each of these is independent, right, because the original ones were independent. And then we could start condensing them, right? So we build this tree where we keep combining independent sources to get a new semi-random sources with fewer and fewer rows. And you see that if the original ones were all aligned, then in the next level they're all aligned, right? And eventually we get down to one row, which is just a uniformly random string, and then we're done. Okay, but this extractor is not very good. If you wanted to do this, there are polynomial number of rows. You would need to do this, logarithmic depth, and so we need a polynomial number of sources, which is pretty bad. Okay, but there is a way to save the situation. So here's another trick that you can use. You can again use strong-seeded extractors to kind of transfer the quality of some random sources. So what do I mean? Suppose you have 3 independent sources. One of them is a semi-random source, and the other 2 you don't know anything about. Then you can use a strong-seeded extractor to obtain from this 2 aligned independent semi-random sources, which had the same number of rows as the original semi-random source. Okay. So the idea is, what you would do is you would view the semi-random source as a list of candidate seeds, and then use each row to extract from one of the sources. So you would use the top row here as a seed to the strong-seeded extractor to extract from A to get the first row here, and so on.
Wait, just go on. I missed
Okay.
someplace else, so just go over that.
So what's the construction is we're viewing this as a list of 3 possible seeds. And what we're going to do is run our strong-seeded extractor with each of the seeds for each source. So here, we'll use the first seed with A to get the first row, the second seed with A to get the second row, so on. Okay. So now, so what do we know that if you picked a uniformly random seed, the output is uniformly random, right? So what you would expect is, on this side, you get a semi-random source. The third row should be uniformly random because you're using a uniformly random seed, right? Okay, but what's not so clear is, so in this way you'll get 2 semi-random sources, but they're not independent, right? Because you used the same seed for both of them. Okay, but they're good enough. When you fix the seed to a typical value, right? What happens? So condition on any fixing of the seed, now these 2 distributions are independent. And by the strong-seeded extractor property, even condition on the seed, for most values of the seed, what you will get here is a semi-random source and another semi-random source, right? So you can think of it as, right? So for most values of most values that you see in this random row, the extractor function is a good extractor for both sources A and B simultaneously. Right? So for fixing of the seed to such a value, what you will get is two independent aligned semi-random sources. All right. So now how would you use this? So here's how you could use this. You can start with just two general sources which are independent. Then again apply our first trick to convert them to aligned semi-random sources. Okay. Apply our second trick to reduce the number of rows. And now, once we've improved the semi-random source that we're working with, we can use this latest trick to get two semi-random sources which are aligned and now have the same number of rows as this source.
With high probability, depending on
right, with high probability.
Specific seed.
Right. So okay, so maybe I should say, so it's good enough that the distributions we're working with are convex combination of independent distributions. Because any extractor that works for two independent sources will also work for a convex combination of two independent sources. So what we'll get here is they're not truly independent, but they're a convex combination of independent aligned semi-random sources. So everything that we want to do will still work. So they're new sources. So far we've used 4 sources.
So you used 4 to get 2, so that's
right.
So far it's not that big. No, but you will repeat it now.
Yeah, we'll
just repeat it now. So the next step, so what do you all say?
Yeah, so then we'll condense again and keep going. And the point is, so before we had this tree, right? So if we needed to condense log n times, we used a polynomial number of sources. And now, right, now to condense log n times, we'll use order log n sources. Right? We're not doing this tree kind of thing. We're improving the situation much faster. Okay, so this already gives an extractor for order log n sources. And this is also this is something that was not known before. So that's the first result.
Actually pretty simple to get such a big improvement.
Yeah, it is pretty
I mean,
simple.
I'm not saying it's simple for you to have found, but
No, it's,
once you found it,
it's very
not
simple compared to
some of the things that
some of
people
this
were doing.
yeah. But I mean, you have to, I guess, it just piggybacks on the whole technology of seeded extractors. So that's the. Okay, so you can get an extractor for order log n sources even when the min-entropy is small, this polylogarithmic. All right. Now returning to your question. So we're going to do better than this extractor, and the way we'll do it is by improving our condenser. So what we'll manage to do is build an extractor for 3 aligned semi-random sources, as long as the sources have a certain shape. So if each source has min-entropy of k and rows of length k, and say the number of rows is much smaller, say square root k in this case, then we'll actually be able to extract from these 3 sources. Okay.
Wait, so there's no n around here?
The n is k times square root k. Okay. So I'll first say how we'll use this. If we had such an object, and then I'll return to describing how we build this. Okay. So suppose we had an extractor that could do this. So given 3 aligned semi-random sources, which where the semi-random sources have fewer rows than the length of each row. Okay. So the length of the number of rows is significantly smaller than the length of each of the rows. Okay. What you would do is the following. So if you would get a much better condenser. So if you started off with aligned sources, say 3 aligned sources which have t rows each, what you could do is now again break up the sources into chunks, right? Where each chunk here contains square root k rows, and then apply that extractor from the last slide, horizontally, right? So in this way you would get t over square root k different outputs, and in the part that contained the aligned random row, you would get a uniformly random output. Okay. So now you get a condenser that, given three sources, reduces the number of rows by a factor of square root k instead of just 2 we had before. Okay. So putting this back into the big picture, even if you didn't use some of the tricks we used before, we could just start with a bunch of sources and convert them to polynomial align some random sources with a polynomial number of rows, and then use this condenser, right? And how long would it take? Well, if your min-entropy is polynomially large, in each step you're reducing the number of rows by square root k, which is again another polynomial. So in just a constant number of steps, you'll be down to just a single row. So this would knock out the whole problem, at least for polynomial min-entropy. Okay, but actually we could do slightly better. If you want to work with lower min-entropy, you could do the same thing we did before. Start with 3 sources, convert them into somewhere random sources with a polynomial number of rows, and then apply our condenser. This would reduce the number of rows by say a square root k factor. Then use 3 more sources to get 3 aligned somewhere random sources which have the same number of rows, and repeat. And in this way you get an extractor for order log n over log k sources with min-entropy k. Okay.
And before it was just log
Log
n,
n.
and now
Just log n.
it was
Right.
just log n.
Yeah.
That's log n over log k.
Yeah, this same, right. Okay, so that's the main result. An extractor for log n over log k sources. K can be polylogarithmically small. And if k is a polynomial, then it's an extractor for a constant number of sources. Okay. Okay, so the only part I haven't shown you yet is this bit. So you have 3 independent aligned summa-random sources. And you know that they have few rows in the sense that the number of rows is significantly smaller than the length of each row. And how do you extract them? So the way we'll extract is again by building a condenser. Except this time we'll do better. So in each step, we'll start with some summa-random sources, say sources with rows of length r and t rows. And each step we'll output, this time 3 sources, which have much improved dimensions. So we'll reduce the number of rows by a factor of 2, and we'll not lose too much in the length of the rows. So previously we were always, when we built a condenser, we started with, say, a collection of independent sources, and we output a single source. Somehow here we'll be able to save on the independence. So we again get 3 things which are independent. Okay. So now once you have this, then you keep repeating, and eventually you'll end up with just single rows, and we'll be done. Okay.
Just giving up a little bit on the length, we're able to keep,
Well, it's a lot on the. Yeah. So we'll crucially need that the entropy is so much more than.
that you can keep making rows shorter and shorter almost.
Right.
I wouldn't even that just sounds
This
wrong.
output adds not
Yeah, it will be larger than t.
Okay. Yeah, I somehow, yes, that's what was bothering me. Somehow I was thinking that r to the epsilon was much smaller than t, and it just sounded impossible. Okay.
R is much larger.
Right, r is large, but still, it still sounds almost impossible. So good. Okay. Good. Okay.
Right.
I'm not doubting your proof. I'm just trying to.
Yeah.
understand.
Okay. All All right, so that's what we're going to do. And, let's see how to do it. So the construction is symmetric in some way. So I'll just show you how to convert A into a sum-random source with fewer rows, and then you do the same thing, to convert the other two. So here's what we're going to do. We're going to use B and C somehow to convert A into a sum-random source with fewer rows. Right?
A, B, and C are independent?
A, B, and C are independent.
So the resulting ones are non-independent?
The resulting ones will be convex combinations of independent sources, so they're as good as independent. Okay, so we'll think of them. So what we'd really like is 3 independent sources. What we'll get is 3 sources which are convex combinations of being exactly independent.
So what if your first 3 would be convex? So now you want to tell us how this works. The first 3 are not independent, but just convex combinations.
That's fine. That works too.
Okay.
Even if, right? So you start with any convex combination of independent sources. You end up with convex combination of independent sources with these properties. So 3 independent sources are a special case of convex.
But even for the regular condensing.
Should be different.
It's invertible convex combination probably. What he means probably is invertible convex combination. Like not the same convex combination.
It won't be the same convex combination. Otherwise, you could have the same. You should have some additional property.
Maybe I don't understand.
It's a convex combination on this product space. It's not that each one is a convex combination. The whole distribution on the product space is a convex combination of...
Convex combination meaning distribution on distributions.
I see. Okay.
So it's a convex combination of distributions. Each distribution is independent, has a property that has independence in it.
But you're going to use B and C to extract from A and then change the roles?
Then we'll use A and C to extract from B, and so on. So we'll introduce dependencies, but somehow we'll be able to control the dependencies.
It will still be a convex combination of I and A.
Right. It'll be a convex combination of sources which are exactly look like this. There's some are random.
Min-Entropy will then be R minus R to the epsilon.
Well, the length will also be smaller, so you'll be uniformly random in this row, inside the convex combination. We'll see. Maybe. Okay. So here's the construction, and I think it'll be more clear what's going on. Okay. The first step is we'll take B and C, and we'll just cut a small slice of the bits from each of these 2 sources. So we'll just take the first few bits of each row from B, and the first few bits of each row from C, and I've just written them down again.
First. That's okay.
Right,
We've got a lot of Israelis here. They weren't totally comfortable with that.
Oh, it's also fun to the set.
It's that's what's important, right? Yeah.
Okay. And then we just apply our old condenser, the XOR condenser, to these 2 sources. Now, because B and C were independent sum-random sources, these 2 here are also independent sum-random sources, and so we just XOR, pairs of rows, and what we get is a single sum-random source, right, with fewer rows. Now, we just view this single sum-random source as a list of candidate seeds to extract from A. Okay, so now we have 3 seeds here, and we use each one to extract from the entire source A. Okay, so at this point we're not using anything about the structure of A. So we just know that A is a source that has some Min-Entropy. So we use a strong seeded extractor with each of these seeds to extract from the entire source. Okay. Okay, so that's the entire construction. So what we end up with is now T over 2 rows in the output for A.
So can you explain why, when you do this and then permute, you get something that's a convex combination of independent?
We'll see. We'll get there. So let me just.
A different piece at the end, right?
No, actually, we'll use the same one. We'll see. Okay, so here's the construction again. So basically, right, so let's step back and see the whole thing. So we somehow use B and C, and these parts of B and C to produce a list of seeds for A, and the same for each of them. And then we use the corresponding seeds to extract from the sources that we start off with.
Just why aren't we just using separate parts phonetically simpler to understand, or do you save anything significant by using the same?
Because all of these parts that we're using is entropy that's going to be lost for the construction. So you'll see, how do you analyze this is the question.
Up to constant factor, you use the same entropy. I mean,
As
you can have, I'm saying, what's
yeah, you could use.
What's so bad about using twice as much entropy?
Nothing is bad except that it buys you nothing, and
Okay.
so it might give you a comfortable feeling in a misleading way. So it's not the issue is that there are dependencies here, and you have to fix it anyway. So you don't really gain anything by.
It may help the referee, but it doesn't help you.
Right. Maybe yeah.
It doesn't help mislead the referee.
Right. Right. The real issue is that, I mean, okay, so there are all kinds of dependencies here. If you use bits from here, it might be that, for instance, there are bits here that are just copying the bits over here. So it's misleading to think that if you move over, to a different slice, you're getting something different, because the dependence is arbitrary.
Just in the one row.
In that one row, everything is independent, but
the other rows
have arbitrary. Okay, so let's think about. Okay, so the first thing to note is. Okay, so let's move to the analysis. Right. So first of all, we have made progress, at least in the sense that the output has fewer rows than before, and is as long as were before, pretty much. And further, if you look at each one of these distributions, right, we've already seen that this list of seeds is a summa-random source, right? It's independent of A, right? It was generated only using B and C. And so this distribution here, by the properties of the strong-seeded extractor, is summa-random, right? The random row here with high probability will give you a good function to extract from A, and so what you get is a summa-random source. Okay, so that's good so far. The problem is independence, right? So what we have on the right here are three sources which are each summa-random and have fewer rows than we started out with, but they could be dependent in arbitrary ways, right? Somehow we want to ensure that there's independence. And so the crucial point is somehow that all the interaction between the sources goes through these a small number of bits. Only these bits in this slice, right? So what do I mean? Let's consider the bits in this variable z, right? All the slices that we used. Now when you fix z, what happens? So condition on z being fixed to some value, all the seeds are fixed, and now everything in the output is only a function of one of the sources, right? So condition on z, you have three independent sources. Okay, but now, condition on z, we don't know what these sources look like, right? It's not clear that now we have three aligned summa-random sources. We just have independence. Okay, and the point is that we'll manage to argue that for most fixings of z, what you get, in fact, is three independent aligned summa-random sources. Okay. So that's what we'll show. So we'll show that for typical values that you get here, you still have summa-random sources on the right, and they're independent because, for fixing of these, each one is a function of only one of the inputs. Okay, so this is what we really want to show. We want to show that the distribution, the the output distribution of applying the strong seeded extractor on the source A given Z equals this fixing, and the seed S A given Z equals Z is somewhere random and aligned with the others. Okay, so just spend some time talking about how to prove this. So the basic idea is we're going to use a union bound. Okay, so there are two basic ways in which this can fail. First, it might be that the value little z that we get is such that A loses a lot of entropy conditioned on this value. So it might be that A given z equals little z has very low entropy. In this case, you cannot hope to have a random row here. Okay. The second way it can fail is it might be that the seed that you get, which is a fixed seed, is a bad seed to extract from the source A given z equals z. Right? Right. So as long as we have both that A has high entropy and that this seed is a good seed, then we're done. Right? Then this will be a somewhere random source. And the point is that both of these events happen with really low probability. So these are kind of standard extractor arguments, but if you right, so imagine that we took a slice of width only W, then the number of bits in this region is only t times W, right? So you'd expect, that the min-entropy of A is to start out with is R. It has R bits of entropy. And so what you expect is when you condition on t times W bits of the source, you expect to lose roughly t times W bits of entropy. And what you can argue is that with high probability, the ZA that you get still leaves, say, R minus 10 times TW bits of entropy. Okay.
Why isn't it just exactly R minus TW? Because your most likely outcome was previously 2 to the minus R, and fixing any particular set of bits.
Well, for instance, it could be.
The different rows of.
It could be that whenever you get the all zero string here, that's the only time you get the all zero string in the rest of. Okay. So then, condition on getting that all zero string, you know exactly what the rest is. You lose. Then the point is that if this little ZA is, if the string carries that much information, then it must be a very low probability string. So the set of all such strings which carry too much information, this bad set has really low weight under the distribution. Okay, so it's an error term. Okay, just kind of written that argument out, but not so enlightening to look at it. Okay, and the second part, to argue that the seed we get is good, first notice that A conditioned on the slices that we're conditioning on is the same as conditioning only on the slice that relates to A, because the other two were independent of A. Okay, so first fix ZA to any value that's good for the previous step. And then now the seed that you're generating is completely independent of A given ZA. And so with high probability, the seed that you generate is going to be good to extract from. Okay. So anyway, the point is that so there are all these bad things that can happen, but all of them are low probability events. And then just by the union bound, we get that for most fixings, none of the bad things happen, and we get what we want. Okay. All right. So that's pretty much it. Just to remind you, so the overall construction looks like this. You start out with a collection, say 3 sources, which are general, and then apply a strong seeded extractor to convert them into aligned somewhere random sources. And then we'll do our improved condensing, which will also involve smaller bits of condensing. So we'll break up the sources into chunks and do this thing over and over, and eventually end up with a single somewhere random source which has much fewer rows, and then repeat this whole thing. Okay. Okay, so that's that. Just to tell you some of the other consequences of this this work. So it turned out that this operation of extracting from some random sources was used in other works. So just plugging these techniques into other papers, there were a few improvements. It helped to improve the output length and error of other extractors and dispersers. And also another result, which didn't seem so important in the beginning, was an extractor for just two blockwise sources. These are other kinds of sources that eventually this was useful in, this helped to get a new Ramsey graph construction, something else that I was working with. All right. So that's the outline. I mean, that's all I'd say about techniques and what's left to do. I think the biggest open question in this area is what can you do just for two sources? And in a long time, the best result is still pretty bad and hasn't shown a lot of progress. So the best extractor for two sources still requires entropy that's not even linear. It's 0.499 times n.
Is there any lower bound of what you could not do?
No, not that I know of. I mean, right, a random function can do log n here.
Okay,
so there are functions. There are functions, but if you, in terms of polynomial time computable functions, then you don't know where the line is. Okay, another result that would be useful and improve some other results is so if you could get an extractor for a constant number of sources, but that worked for polylogarithmic min-entropy as opposed to just polynomial min-entropy, then this would actually have an impact on some other things. It would have an impact on the Ramsey graph. That's what I'm thinking about.
What kind of impact would it have?
It would improve the Ramsey graph. So the Ramsey graph.
Multi-part,
right? Sorry.
Multi-part, right?
No. There's a plain Ramsey. We have a Ramsey graph construction, a new construction which avoids. So Ramsey graph is a graph which doesn't have, either large cliques or large independent sets, and we have a construction that avoids cliques and independent sets, of size. If the graph is of size 2 to the n, it avoids cliques and independent sets of size 2 to the n to the epsilon. And it would improve this parameter. So you would get better graphs that avoid even smaller cliques and independence. Okay, that's it.